Chapter 5, Regression. In this chapter, we continued the exploration of the relationships between two variables that we began in Chapter 4. In Chapter 4, we saw that a useful tool for exploring the relationship between two variables is the scatter plot. When the relationship is linear, correlation is a numerical measure of the strength of the linear relationship. In this chapter, we introduce a method for summarizing the straight line relationship between two variables when it exists. When there is a clear explanatory variable and a strong straight line relationship, it is tempting to assume that large values of the correlation imply that there is a cause and effect relationship between the explanatory variable and the response variable. This need not be true. Correlation does not imply causation. In this chapter, we explore this issue more carefully. Linear, straight-line relationships between two quantitative variables are easy to understand and quite common. In Chapter 4, we found linear relationships in settings as varied as Florida manatee deaths, the risk of cancer, and predicting tropical storms. Correlation measures the direction and strength of these linear relationships. When a scatter plot shows a linear relationship, we would like to summarize the overall pattern by drawing a line of best fit, called a regression line, on the scatter plot. 5.1 Regression lines. A regression line summarizes the relationship between two variables, but only in a specific setting, when one of the variables helps explain or predict the other. That is, regression describes a relationship between an explanatory variable and a response variable. Regression line. A regression line is a straight line that describes how a response variable y changes as an explanatory variable x changes. We often use a regression line to predict the value of y for a given value of x when we believe the relationship between y and x is linear. Example 5.1. Does fidgeting keep you slim? Why is it that some people find it easy to stay slim? Here, following our 4-step process, page 62, is an account of a study that shed some light on gaining weight. State, some people don't gain weight even when they overeat. Perhaps fidgeting and other non-exercise activity, NEA, explains why. In fact, some people may spontaneously increase non-exercise activity when fed more, thus reducing the amount of weight they gain from overeating. To investigate the effect of NEA on fat gain, researchers deliberately overfed 16 healthy young adults for 8 weeks. They measured fat gain in kilograms and, as an explanatory variable, change in energy use in calories from activity other than deliberate exercise, fidgeting, daily living, and the like. Change in energy use was energy use measured the last day of the 8-week period, minus energy use measured the day before the overfeeding began. Here are the data. Do people with larger increases in NEA tend to gain less fat? Plan. Make a scatter plot of the data and examine the pattern. If it is linear, use correlation to measure its strength and draw a regression line on the scatter plot to predict fat gain from change in NEA. Solve. Figure 5.1 is a scatter plot of these data. The plot shows a moderately strong negative linear association with no outliers. The correlation is R equals negative 0.7786. Figure 5.1, fat gain after 8 weeks of overeating, plotted against NEA, increase in non-exercise activity over the same period. For example, 5.1. So when you look at the scatter plot, you can see on the x-axis is non-exercise activity change in calories, y-axis is fat gain in kilograms. You can see the line of best fit, which is a negative correlation. You can see the regression line predicts fat gain from NEA. And then if you go to like 400, and then you, from the bottom, and then you touch the linear regression line, and then you make a square and you go over to the fat gain. This is the predicted fat gain for a subject with NEA equals 400 calories. The line on the plot is a regression line for predicting fat gain from change in NEA. Conclude, people with larger increases in NEA do indeed gain less fat. To add to this conclusion, we must study regression lines in more detail. We can, however, already use the regression line to predict fat gain from NEA. Suppose that an individual's NEA increases by 400 calories when she overeats. Go up and over on the graph in figure 5.1 from 400 calories on the x-axis, go up to the regression line and then over to the y-axis. The graph shows that the predicted gain in fat is a bit more than 2 kilograms. Many calculators and software programs will give you the equation of a regression line for keyed-in data. Understanding and using the line are more important than the details of where the equation comes from. Review of straight lines. Suppose that y is a response variable plotted on the vertical axis, and x is an explanatory variable plotted on the horizontal axis. A straight line relating y to x has an equation of the form y equals a plus bx. In this equation, b is the slope, the amount by which y changes when x increases by 1 unit. The number a is the intercept, the value of y when x equals 0. Example 5.2, using a regression line. Any straight line describing the NEA data has the form fat gain equals a plus b times NEA change. The line in figure 5.1 is the regression line with the equation fat gain equals 3.505 minus 0.00344 times NEA change. Be sure you understand the role of the two numbers in this equation. The slope b equals negative 0.00344 tells us that, on average, fat gained goes down by 0.00344 kilograms for each added calorie of NEA change. The slope of a regression line is the rate of change in the response on average as the explanatory variable changes. The intercept a equals 3.505 kilograms is the estimated fat gain if NEA does not change when a person overeats. The equation of the regression line makes it easy to predict fat gain. If a person's NEA change increases by 400 calories when she overeats, substitute x equals 400 in the equation. The predicted fat gain is fat gain equals 3.505 minus 0.00344 times 400 equals 2.13 kilograms. This is a bit more than 2 kilograms, as we estimated directly from the plot in example 5.1. When plotting a line on the scatter plot, use the equation to find the predicted y for two values of x, one near each end of the range of x in the data. Plot each y above its x value and draw the line through the 2 points. The slope of a regression line is an important numerical description of the relationship between the two variables. Although we need the value of the intercept to draw the line, this value is statistically meaningful only when, as in example 5.2, the explanatory variable can actually take values close to 0. The slope b equals negative 0.00344 in example 5.2 is small. This does not mean that change in NEA has little effect on fat gain. The size of the slope depends on the units in which we measure the two variables. In this example, the slope is the change in fat gain in kilograms when NEA increases by 1 calorie. There are 1,000 grams in a kilogram. If we measured fat gain in grams, the slope would be 1,000 times larger, b equals negative 3.44. You can't say how important a relationship is by looking at the size of the slope of the regression line. 5.2, the least squares regression line. In most cases, no line will pass exactly through all the points in a scatter plot. Different people will draw different lines by eye. We need a way to draw a regression line that doesn't depend on our guess of where the line should go. Because we use the line to predict y from x, the prediction errors we make are errors in y, the vertical direction in the scatter plot. A good regression line makes the vertical distances of the points from the line as small as possible. Figure 5.2, the least squares idea. For each observation, find the vertical distance of each point on the scatter plot from a regression line. The least squares regression line makes the sum of the squares of these distances as small as possible. Figure 5.2 illustrates the idea. This plot shows 3 of the points from figure 5.1 along with the line on an expanded scale. The line passes above one of the points and below 2 of them. The 3 prediction errors appear as vertical line segments. For example, one subject had x equals negative 57, a decrease of 57 calories in NEA. The line predicts a fat gain of 3.7 kilograms, but the actual fat gain for the subject was 3.0 kilograms. The prediction error is error equals observed response minus predicted response equals 3.0 minus 3.7 equals negative 0.7 kilograms. There are many ways to make the collection of vertical distances as small as possible. The most common is the least squares method, least squares regression line. The least squares regression line of y on x is the line that makes the sum of the squares of the vertical distances of the data points from the line as small as possible. One reason for the popularity of the least squares regression line is that the problem of finding the line has a simple answer. We can give the equation for the least squares line in terms of the means and standard deviations of the two variables and the correlation between them. Equation of the least squares regression line. We have data on an explanatory variable x and a response variable y for n individuals. From the data, calculate the means x bar and y bar and the standard deviations s and s of the two variables and their correlation r. The least squares regression line is the line with slope y hat equals a plus bx, b equals r times sy divided by sx, and intercept a equals y bar minus b times x bar. We write y hat, red y hat, in the equation of the regression line to emphasize that the line gives a predicted response y hat for any x. Because of the scatter of points about the line, the predicted response will usually not be exactly the same as the actually observed response y. In practice, you don't need to calculate the means, standard deviations, and correlation first. Software or your calculator will give the slope b and intercept a of the least squares line from the values of the variables x and y. You can then concentrate on understanding and using the regression line. 5.3 Examples of technology. Least squares regression is one of the most common statistical procedures. Any technology you use for statistical calculations will give you the least squares line and related information. Each output records the slope and intercept of the least squares line. The software also provides information that we do not yet need, although we will use much of it later. Be sure that you can locate the slope and intercept on all four outputs. Once you understand the statistical ideas, you can read and work with almost any software output. Facts about least squares regression. One reason for the popularity of least squares regression lines is that they have many convenient properties. The least squares regression line is the line that makes the vertical distances of the data points from the line as small as possible. Here are some additional facts about least squares regression lines. Fact 1. The distinction between explanatory and response variables is essential in regression. Least squares regression makes the distances of the data points from the line small only in the y direction. If we reverse the roles of the two variables, we get a different least squares regression line. Fact 2. There is a close connection between correlation and the slope of the least squares line. The slope is b equals r times sy divided by sx. Example 5.3, predicting fat gain, predicting change in NEA. Figure 5.4 repeats the scatter plot of the NEA data in Figure 5.1, but with two least squares regression lines. The solid line is the regression line for predicting fat gain from change in NEA. This is the line that appeared in Figure 5.1. We might also use the data on these 16 subjects to predict the change in NEA for another subject, based on that subject's fat gain when overfed for 8 weeks. Now the roles of the variables are reversed. Fat gain is the explanatory variable, and change in NEA is the response variable. The dashed line in Figure 5.4 is the least squares regression line for predicting NEA change from fat gain. The two regression lines are not the same. In the regression setting, you must know clearly which variable is explanatory. You see that the slope and the correlation always have the same sign. For example, if a scatter plot shows a positive association, then both b and r are positive. The formula for the slope b says more. Along the regression line, a change of 1 standard deviation in x corresponds to a change of r standard deviations in y. When the variables are perfectly correlated, r equals 1 or r equals -1, the change in the predicted response y hat is the same in standard deviation units as the change in x. Otherwise, because r is between -1 and 1, the change in y hat in standard deviation units is less than the change in x in standard deviation units. As the correlation grows less strong, the prediction y hat moves less in response to changes in y. Fact 3. The least squares regression line always passes through the point x bar or y bar on the graph of y against x. This is a consequence of the equation of the least squares regression line. In exercise 5.5, we ask you to confirm this. Fact 4. The correlation R describes the strength of a straight line relationship. In the regression setting, this description takes a specific form. The square of the correlation, R squared, is the fraction of the variation in the values of y that is explained by the least squares regression of y on x. The idea is that when there is a linear relationship, some of the variation in y is accounted for by the fact that as x changes, y changes along with it. Look again at figure 5.1, page 125, the scatter plot of the NEA data. The variation in y appears as the spread of fat gains from 0.4 to 4.2 kilograms. Some of this variation is explained by the fact that x change in NEA varies from a loss of 94 calories to a gain of 690 calories. As x changes from negative 94 to 690, y changes along the line. You would predict a smaller fat gain for a subject whose NEA increased by 600 calories than for someone with zero change in NEA, but the straight line tied to y of y to x doesn't explain all of the variation in y. The remaining variation appears as the scatter of points above and below the line. Although we won't do the algebra, it is possible to break the variation in the observed values of y into two parts. One part measures the variation in y hat along the least squares regression line as x varies. The other measures the vertical scatter of the data points above and below the line. The squared correlation r squared is the first of these as a fraction of the whole. R squared equals variation in y hat along the regression line as x varies, divided by total variation in observed values of y. Example using r squared. For the NEA data, r equals negative 0.7786 and r squared equals negative 0.7786 squared, which is negative 0.7786 times negative 0.7786 equals 0.6062. About 61% of the variation in fat gained is accounted for by the linear relationship with change in NEA. The other 39% is individual variation among subjects that is not explained by the linear relationship. Figure 4.3, page 105, shows a stronger linear relationship between boat registrations in Florida and manatees killed by boats. The correlation is r equals 0.919 and r squared equals 0.919 squared equals 0.845. About 85% of the year-to-year variation in number of manatees killed by boats is explained by regression on number of boats registered. Only about 15% is variation among years with similar numbers of boats registered. You can find a regression line for any relationship between two quantitative variables, but the usefulness of the line for prediction depends on the strength of the linear relationship. So r squared is almost as important as the equation of the line in reporting a regression. All the outputs in figure 5.3 include r squared either in decimal form or as a percentage. When you see a correlation, square it to get a better feel for the strength of the association. Perfect correlation, r equals negative 1 or r equals 1, means the point lies exactly on a line. Then r squared equals 1, and all the variation in one variable is accounted for by the linear relationship with the other variable. If r equals negative 0.7 or r equals 0.7, r squared equals 0.49, and about half the variation is accounted for by the linear relationship. In the r squared scale, correlation of plus minus 0.7 is about halfway between 0 and plus minus 1. Facts 2, 3, and 4 are special properties of least squares regression. They are not true for other methods of fitting a line to data that are discussed in more advanced courses.